Hello everyone. Today we are going to discuss about the Schrodinger's equation, one of the most important equation of the engineering physics. Let's move ahead. Schrodinger's equation gives us three important factors. The first one is the energy of the particle. The second one is the behavior of the particle over the time, and the third one is the position of the particle. But the interesting factor is that in the quantum mechanics, we cannot find the exact position of the particle because the particle is not like in a solid ball. It behaves like a wave. It have the wave nature. So finding the exact position is not possible. But the Schrodinger's equation helps us to know the position, the highest probability of the particle to be present at the specific position. Schrodinger's equation gives us a variable which is pronounced as the psi and denoted as shown in the figure. But the important thing is that we cannot find the value of this psi. So what we can calculate? We can calculate the psi square. Psi square helps us the probability of the particle to be present at any specific position. Let's understand how we find it. Uh, we can say that a particle may be present at that position where the density of the psi square is the maximum. Let's take an example. If there is a room and few peoples are in the room, and in the room some places are dark and some places are bright, so there is a highest probability of the people to be present at that place where there is a plenty of the light, means the place is the bright. Similarly to that, we can say that the electron may be present at that place where the density of the psi square is maximum. So this is the explanation of the Schrodinger's equation. Now we will move toward the explanation of the derivation. Now we start with the wave function psi of x comma t, where psi is the wave function, x is position, t is time, a is amplitude, k is wave number, and omega is the angular frequency. You can see the wave function on the slide. Now take the derivative with respect to time. So when we derivate it with respect to time, we get it equals to negative of I into omega into the psi. Now multiply both the side by I into the h bar, where h bar is the reduced Planck's constant and its value is equals to h divided by 2 pi. Here h is known as the Planck's constant. So now I into h bar into the derivative of the psi with respect to t will become equals to h bar into omega into the psi. We know that energy E is given by E equals to h bar into the omega. So I into h bar into derivative of the psi with respect to time is equals to E into the psi. Now take the derivative with respect to the position, means with respect to the x. So the derivative of psi with respect to x is equals to I into k into the psi. Now multiply both the side by negative of I into the h bar. So negative of I into the h bar into derivative of psi with respect to x will become equals to h bar into k into psi. As we all know that momentum p is given by p is equals to h bar into the k. So negative of I into h bar into the derivative of the psi with respect to x will become equals to p into the psi. So now using the energy relation, that is E is equals to p square divided by 2m plus v, where m is mass and v is a potential energy, substitute the operation and then we get the following equation. So now the final Schrodinger's equation will be I into the h bar into the derivative of psi with respect to time is equals to negative of square of h bar divided by 2m into derivative of psi, double derivative of psi with respect to x plus v into the psi. That's for today. Thanks a lot.